Hello, this is Stefan again from schristoph.online. Today we'll talk about my latest blog post on a counterintuitive result. Your cheapest model should write your agent's harness while your most expensive model runs it. It's based on a recent paper and I reproduced the core mechanism on Amazon Bedrock. Let's dig in. The key insight is that a self-evolving agent has two distinct jobs that people usually conflate. The evolver reads execution evidence, the failures and traces, and writes an update back into the harness. The solver then uses that updated harness to solve the next task. End-to-end scores hide which one is actually doing the work. So the paper fixes one role and buries the other. Now you might ask yourself, evolver versus solver, which is which exactly? Think of it like this. The evolver is the model that writes the harness update from evidence. The solver is the model that then uses that harness to actually do the task. The whole paper rests on measuring those two roles separately instead of blurring them into one end-to-end score. And here's the paper itself. On arXiv, it's titled Harness Updating is Not Harness Benefit by Lin and co-authors from Penn State, UC Santa Cruz, and Amazon, arXiv 2605-30621. This is the primary source for the whole post. The abstract right here lays out the disentangling of evolution capabilities that everything I'm about to walk through is built on. And this is the code that goes with it from the AVivo lab. The repository here contains the implementation behind the experiments across 7 language models and 3 agentic benchmarks. So you have the paper for the claims and the repo for the mechanism. Finding 1. Writing the harness is flat across model tiers. Fix the solver, swap the evolver, and the gains barely move. At most 3.1 percentage points between best and worst. The smallest model in the study, a 9 billion parameter open model, actually posts the highest evolver gain on one benchmark. A tiny model and a frontier model produce skills that are procedurally near identical. Here's the picture of that result. On the left, a 9 billion parameter model writes a skill. On the right, a frontier model writes one for the same task. The two skills are procedurally isomorphic, the same steps in slightly different words. And crucially, the downstream solver gains the same amount from either one. That's what flat looks like. A critical reader will push back here. Isn't this just one paper? Fair, it's a single study, 7 models, 3 benchmarks, and it hasn't been independently replicated yet. So I frame it honestly in the post as what a paper found with the numbers. And I label my own bedrock, run a mechanism demo. Not proof, strong within this study, but worth watching for replication. Finding 2 is the opposite shape. Benefiting from the harness is an inverted U. Mid-tier models gain the most. Strong models sit near the ceiling with little headroom, and weak models gain the least, because they either never load the relevant skill or stop following it as the task gets longer. So you can't just hand a weak model a better harness and rescue it. So you might wonder, why do weak models barely benefit even when you hand them a good harness? The paper measures 2 failure modes. First, activation failure. The weak model loads the right skill only about a quarter of the time, versus almost always for strong models. Second, adherence drift. Even when it loads the skill, it stops following it as the task runs long. Headroom isn't the problem. Using the harness is. I wanted to feel the claim, not just read it, so I built the smallest honest version on Amazon Bedrock. A cheap haiku evolver writing a skill that a stronger sonnet solver then uses. The solver with no skill fails a hidden convention in the task. The cheap evolver reads the verifier labeled feedback, writes a rule into a skill, and the strong solver then passes. The cheap model fixed the expensive one. Here's the honest objection I had to answer. The cheap evolver only wrote the right skill, because I handed it the gold labels. Isn't that cheating? Not quite. Because that label is the verifier signal, which is exactly what real self-evolving loops run on. The nuance I keep in the post is that the cheap evolver matches the expensive one only when the feedback is good. So evidence quality is the real dependency, not model size. The demo runs through the Amazon Bedrock Converse API, documented here. This is what makes swapping a cheap evolver for a strong solver a single model ID change rather than a rewrite, one consistent call shape across every model tier. Setting temperature to 0 is what gives you reproducible skills. So the budget logic flips. Don't pay frontier prices to author skills. Run the evolver on a cheap model in the background, spend on the solver, because that's where the score actually moves, and invest in the verifier, not the evolver, because the cheap author only works when the feedback signal is good. This decision flow sums up the spending rule. Put your cheap model in the evolver seat, keep your strong model in the solver seat, and pour the savings into a better verifier. The diagram is the whole post in one picture. Cheap to write the harness, strong to run it, and a good signal to keep the cheap author honest. And the practical question, what should a team actually do on Monday morning? 3 moves. Move your evolver to a cheap model. Spend the savings on solver capability and a better verifier. And treat every harness update as auditable and reversible, because a cheap author with a weak signal can confidently write the wrong rule. And to run this as real infrastructure, the post points at Amazon Bedrock Agent Core here. Agent Core Gateway turns your existing APIs and Lambda functions into tools the solver can call, while runtime and memory give you somewhere to persist the evolved skills between runs, so you're not rebuilding the harness every time. Thanks for listening. I hope this was helpful. If so, you can reach out on LinkedIn directly to get in touch with me, or head to my blog at schristoph.online. Let's keep in touch. Take care.